The universe sometimes breaks its own rules. What if reality itself glitched, and scientists could not explain why? Across the cosmos, strange signals pulse from the void, and objects move in ways physics says are impossible. These are not stories, they are documented anomalies that challenge everything we know. By the end, you will understand the most baffling cosmic mysteries and the profound questions they raise about our place in the universe. We will journey from a single, shocking signal heard decades ago to the strange drift of spacecraft in deep space. What does it feel like when the familiar laws of nature suddenly fail? One night in 1977, a radio telescope in Ohio picked up a signal that would become a legend. Astronomer Jerry Amon was reviewing printed data when he saw a string of letters and numbers so powerful and so unusual that he circled it in red pen and wrote one word beside it. Wow! This signal, now known as the WOW signal, lasted for 72 seconds. It came from the direction of the constellation Sagittarius, and it was a concentrated burst of radio waves on a frequency that natural cosmic objects rarely use. A frequency that many thought would be ideal for interstellar communication. The signal was incredibly strong, then it vanished, never to be heard again. For decades, scientists have tried to explain it. Some suggested it was a passing comet, but the specific comets proposed were not in the right part of the sky at that time. Others wondered about a military satellite or some bizarre reflection from space junk. But the signal's unique characteristics ruled out these human-made sources. The signal was narrowband, meaning it was focused on one very specific frequency, much like a radio station you tune into. And natural cosmic noise is almost never that precise. Experts like Seth Shostak from the SETI Institute have openly considered if this was our first potential hello from another civilization. The sheer power of the signal implied a transmitter far more powerful than anything we could build, possibly one designed for sending a message across the galaxy. Yet, without a repeat of the signal, the mystery remains frozen in time. Why only once? What could possibly produce such a brief, intense, and targeted shout into the cosmos, only to fall silent forever? The WOW signal stands as a perfect glitch in reality, a one-time event that defies all logical explanation and reminds us that the universe is capable of anything. Just as we grapple with a mysterious signal from the void, our own spacecraft have begun to act strangely, moving in ways that should be impossible. Years later, another profound anomaly arrived from the depths of interstellar space. In late 2017, astronomers in Hawaii spotted a tiny, fast-moving speck of light. They named it Oumuamua, which means scout in Hawaiian. It was the very first object ever detected that came from beyond our solar system. Immediately, it was clear this visitor was unlike anything we had seen before. Its path was not a closed orbit around our sun. It was a hyperbola, a one-way ticket through our neighborhood on its way back out to the galaxy. But its strangeness did not end with its origin. Telescopes struggled to get a clear image, yet by measuring how its brightness changed over time, scientists deduced its shape. It was not round. It was either extremely elongated, like a cosmic cigar, or remarkably flat, like a pancake. This was bizarre, as most natural objects in space are roughly lumpy or spherical due to gravity. Then came the real shock. As Oumuamua sped away from the sun, it did something impossible. It accelerated, not from the pull of a planet's gravity but on its own. This is called non-gravitational acceleration. For a comet, this is normal, caused by the sun's heat vaporizing ice and creating jets of gas that push it along. But Oumuamua had no coma, the fuzzy cloud of gas and dust that surrounds a comet, and no visible tail. It was as dark and barren as a rock, yet it was speeding up like a spaceship firing its engines. This single observation sent shockwaves through the scientific community. How could a silent, dark rock accelerate without any visible exhaust? Leading astronomers like Harvard's Avi Loeb proposed a radical idea. What if Oumuamua was not a natural rock at all, but a piece of advanced technology? Perhaps a light sail, a thin structure pushed by the radiation pressure from starlight itself. This would explain its unusual shape and its mysterious acceleration without any need for visible outgassing. Other scientists scrambled for natural explanations, suggesting maybe it was made of solid hydrogen ice, which could sublimate or turn directly from solid to gas in the sun's warmth without leaving a visible trail. Or perhaps it was a shard from a planet torn apart by its star long ago. Yet each theory had holes. Hydrogen ice would not survive a long journey through interstellar space. A simple rock fragment does not explain the extra push. The debate continues to this day. Oumuamua was a true interstellar scout, giving us a fleeting, confusing glimpse of what else is out there. It challenged our categories and forced us to ask if we were looking at a new type of natural object, or something far more profound. This strange acceleration in the void of space is not an isolated mystery. We have witnessed a similar, persistent anomaly much closer to home, with our own robotic explorers. Far from the strange journey of Oumuamua, a more familiar set of explorers were quietly defying expectations. The Pioneer 10 and 11 spacecraft, launched in the early 1970s, were pioneers in every sense. The first to travel through the asteroid belt, and the first to send back close-up images of Jupiter and Saturn. For years, they sailed outward, beaming data back to Earth as they headed for the void beyond our solar system. Yet as they traveled, a tiny, persistent error began to appear in their navigational data. They were slowing down just a little bit more than anyone had predicted. This minuscule deceleration, a drift almost too small to measure, became known as the Pioneer Anomaly. It was a deviation so slight it would not have bothered a human pilot, but for the scientists tracking the probes with exquisite precision, it was a glaring inconsistency. According to the known laws of gravity, the pull from the sun and planets should have accounted for their speed exactly, but something was tugging on them, an unknown force equivalent to a 10 billionth of a gravity here on Earth. For decades, this glitch haunted the physics community. Was it evidence of a flaw in Einstein's theory of general relativity? Could it be the gravitational pull of unseen dark matter, or perhaps something entirely new, a fundamental force we had not yet discovered? The mystery captivated researchers like Slava Turishev, who led a monumental effort to recover and analyze decades-old data, from magnetic tapes to vintage mission logs. His team painstakingly built a digital model of the Pioneer spacecraft, and they found a surprisingly mundane culprit. The probes were powered by radioactive plutonium, and the heat they emitted was not perfectly symmetrical. A tiny, anisotropic push from this thermal radiation, radiating more from one side of the spacecraft than the other, was acting like a faint, constant break. This explanation, while elegant, did not completely erase the anomaly's profound impact. Why did this thermal effect only show up so clearly in the Pioneer probes and not others, like the Voyager spacecraft? The answer lay in their unique design and stability. Unlike Voyager, which used thrusters to spin-stabilize itself, the Pioneers were simple spinners, their orientation fixed, allowing the subtle, one-directional push of heat to build up over time into a measurable drift. The Pioneer Anomaly taught us a vital lesson. It showed that even in the vast, silent expanse of space, the smallest details matter. A little heat, a simple engineering choice, could create a mystery that looked like new physics. It forced us to look more carefully at our own creations and to question our assumptions about the emptiness they travel through. This case of a subtle, persistent drift reminds us that not all cosmic glitches are grand, singular events. Some are quiet, cumulative, and hidden in plain sight. waiting for the right mind to uncover their secrets. And sometimes the glitches are not quiet at all, but sudden, violent, and incredibly powerful bursts of energy from the darkest parts of the cosmos. Deep in the fabric of space, another kind of glitch erupts with unimaginable force. Fast radio bursts are the universe's most powerful short circuits, blasting out more energy in a single millisecond than our sun releases over several days. These are not gentle signals, but violent, cosmic screams that travel for billions of years before a radio telescope on Earth catches their fleeting echo. The first one was discovered in 2007 by astronomer Duncan Lorimer, hidden in old data, and for years it was a solitary mystery. Then, everything changed. Scientists found a burst named FRB 1211-2, and it did something incredible. It repeated. Unlike the one-time wow signal, this source in a distant dwarf galaxy flashed again and again, unpredictably, proving these were not just random, catastrophic explosions. Something or someone was turning the cosmic transmitter on and off. The repeating nature of these bursts shattered the simplest explanation, that they were the final death cries of collapsing stars. A star only dies once. This pointed to a source that could survive its own outburst, a stable and incredibly powerful engine. The leading suspect is a type of stellar corpse called a magnetar, a neutron star with a magnetic field so intense it could strip the information from every credit card on Earth from halfway across the galaxy. Theorists suggest that starquakes on the surface of these magnetars, or sudden magnetic reconnection events, could unleash the titanic energy required. Yet, even this compelling idea struggles to explain the sheer diversity of the bursts now being catalogued by advanced telescopes like CHIME in Canada, which discovers new ones almost daily. Some burst only once, others repeat in chaotic patterns, and their radio waves are stretched and dispersed in different ways as they travel through the sparse matter of intergalactic space. This dispersion measure is a clue to how much material the signal has passed through. Yet the variations are so wild they suggest these bursts originate in wildly different cosmic environments. This has inevitably led to more speculative possibilities. Could these focused, immensely powerful pulses be evidence of advanced technology? Perhaps alien civilizations are powering interstellar light sails with beams of energy so strong we see them across the universe. While most scientists favor natural, if extreme, astrophysical engines, the very fact that such a question can be seriously posed shows how deeply these events challenge our understanding. Each new flash of data brings more questions than answers. How can any natural object be so energetically efficient? What kind of cosmic powerhouse can operate on a millisecond timescale? The mystery of fast radio bursts pulls our gaze to the most energetic and bizarre corners of the cosmos, where the very laws of physics seem to be pushed to their breaking point. And just as we confront these fleeting, energetic anomalies, we must also face glitches of a completely different nature, not in the crackle of radio waves, but in the silent, invisible fabric of gravity itself. But gravity's glitches are not confined to the lonely drift of deep space probes. They show up in a much more active and precise maneuver, one critical to exploring our solar system. When a spacecraft swings by a planet to steal a little orbital energy and boost its speed, the math is supposed to be perfect, yet repeatedly it has not been. This is the Fly-by Anomaly. The first hints emerged in the 1990s with the Galileo spacecraft, which needed 2 gravitational assists from Earth to reach Jupiter. Each time it flew past our world, tracking data revealed a tiny, unexpected change in its velocity. The difference was minuscule, a fraction of a millimeter per second, but for navigators relying on the clockwork precision of orbital mechanics, it was a glaring error. The same strange speed shift was later seen with other missions, like the Rosetta Comet Chaser during its Earth flyby in 2005, and even the Messenger probe on its way to Mercury. Sometimes the spacecraft gained a tiny bit of extra speed. Sometimes it lost a little, as if an unseen hand gave it a gentle, inexplicable push or pull during its closest approach. Scientists immediately began searching for a cause. Was it atmospheric drag? The effect was seen even at altitudes where the atmosphere is vanishingly thin. Could it be the pressure of radiation from the Sun or even from Earth itself? The numbers never quite added up. Perhaps it was a subtle effect of general relativity, a consequence of the planet's rotation dragging spacetime around with it, an effect known as frame dragging. Yet when physicists did the calculations, the predicted influence was far too small to explain the anomaly. The late physicist John Anderson dedicated years to this puzzle, exploring exotic ideas like a halo of dark matter surrounding our planet. If Earth were enshrouded in a fine mist of these invisible particles, their gravitational tug could, in theory, alter a spacecraft's path. But why, then, would the effect be so inconsistent? Some missions, like the Cassini probe to Saturn, showed no anomaly at all. This inconsistency is perhaps the most baffling part of the mystery. It suggests the glitch is not a universal law of gravity, but something conditional. It might depend on the specific trajectory of the flyby, whether the spacecraft approaches over the equator or the poles, or even the unique geometry and materials of the spacecraft itself. Could the craft's own rotation or its internal heat be generating a tiny, unforeseen thrust? We are left with a cosmic riddle hiding in plain sight. Our most trusted force, gravity, appears to have a quirky, unpredictable side during these intricate celestial dances. For future missions traveling to the outer planets, where a single miscalculated flyby could mean missing a target by millions of miles, understanding this glitch is not just academic. It is essential. It forces us to ask if our map of gravity, a force we thought we knew so well, is still missing a few crucial details. And if gravity itself can behave strangely on the scale of a planet, what happens when we look at the very largest structures in the universe? Gravity's subtle quirks during planetary flybys are one thing, but what happens when we look at the very largest structures in the cosmos? There, scientists have found a motion so vast and so strange, it seems to defy the very expansion of the universe itself. Entire clusters of galaxies, thousands of them, are drifting in a coordinated stream, like leaves caught in a slow, cosmic river. This phenomenon is known as dark flow. It was first detected by a team led by Alexander Kashlinsky, who used the universe's oldest light, the cosmic microwave background, as a fixed reference frame. By carefully measuring how these galaxy clusters were moving relative to this primordial glow, they found they were all being pulled in the same direction, toward a point far beyond the edge of our observable universe. The standard model of cosmology tells us that the universe is expanding uniformly, with galaxies drifting apart in a generally random, Hubble-like flow. Dark flow is a glaring exception, a coordinated motion on a scale of billions of light years that suggests something immense is tugging on them from the outside. What could possibly exert such a gravitational pull? The most mind-bending possibility is that this flow is evidence of other universes. In a multiverse scenario, the gravitational influence of a neighboring universe, or a massive structure from a previous cosmic epoch before our Big Bang, could be drawing matter toward it. Skeptics have argued that the data might be contaminated by subtle measurement errors or local effects we do not yet understand. Yet newer observations from powerful telescopes like the Planck satellite have continued to hint at this strange, large-scale drift, keeping the debate alive. Why would countless galaxies move in unison if not pulled by something truly colossal, something we cannot see? This grandest of glitches forces us to confront the limits of our knowledge, suggesting that our entire observable universe might be just a single island in a far vaster and stranger cosmic archipelago. And just as we ponder these immense, invisible currents, we find that even the familiar atmospheres of our planetary neighbors hold their own, more intimate mysteries. Even on the red, dusty plains of Mars, reality seems to flicker. Since 2012, NASA Curiosity rover has been sniffing the thin Martian air, and it has repeatedly caught a ghostly scent, brief but powerful spikes of methane gas. These are not steady background levels, but sudden, localized bursts that appear and vanish without warning. On our own planet, methane is a potent signature. It is a gas largely produced by living organisms, from microbes to cows, or by active geological processes like volcanism. Finding it on a world we thought was geologically dormant and utterly lifeless is like hearing a single, clear note from an instrument in an empty room. The spikes seem to follow a seasonal pattern, rising and falling with the Martian year. And they often occur at night when atmospheric mixing is low, suggesting a nearby hidden source. Scientists like Chris Webster, who leads the rover's methane sniffing instrument, have wrestled with the data. Could there be subterranean reservoirs of the gas, trapped in ice like clathrates, occasionally cracking open to release their contents? Or is it the result of a slow, chemical reaction between certain rocks and water, a process called serpentinization, happening deep below the surface? Yet, every proposed explanation runs into a wall. Mars lacks the widespread volcanic activity we would expect for a geological source, and no one has found definitive proof of Martian microbes. The mystery only deepens when we look from another angle. The European Space Agency's Trace Gas Orbiter, a spacecraft specifically designed to study the Martian atmosphere with incredibly sensitive instruments, has often flown over the same region and detected nothing. It has failed to confirm many of Curiosity's ground-level spikes. This discrepancy is not a simple case of one being right and the other wrong. It points to something far more intriguing. Perhaps the methane is being destroyed incredibly quickly between the ground and the orbiter, broken down by some unknown chemical process in the atmosphere. Or maybe the releases are so fleeting and localized that the orbiter simply misses the short-lived plumes. Each whiff of methane is a tiny, maddening glitch in our understanding of a dead world, forcing us to question if Mars is quietly, secretly, still alive in some way we cannot yet see. But Earth's closest neighbor holds other, older anomalies, ones that have been witnessed not by robots, but by human eyes for centuries. Even our own moon, a constant and silent companion, has its moments of strange illumination. For centuries, astronomers have trained their telescopes on its cratered face only to see it flicker. These are not the flashes of meteor impacts, but something more mysterious, brief glows and color changes that appear and vanish on the barren surface. These events are known as lunar transient phenomena. One of the most active sites is the Aristarchus crater, a brilliant, deep gouge in the lunar soil that has been seen to flash with crimson glows and hazy obscurations for over 200 years. Even the Apollo astronauts joined in the watch. The crew of Apollo 11 reported a bright patch in the Aristarchus region, and Mission Control confirmed that amateur astronomers on Earth were seeing it at the very same time. What could possibly cause a dead world to light up like this? The leading theories point to natural, if poorly understood, processes. One strong candidate is outgassing, where trapped radioactive gases like radon seep from deep below the surface, disturbing the fine lunar dust and causing it to glow or temporarily change its appearance. Another possibility involves the moon's interaction with the solar wind, that constant stream of particles from the sun. When these charged particles strike the lunar soil, they might build up tremendous electrostatic charges, eventually discharging in a sudden, silent spark visible from Earth. Yet, the erratic nature of these events defies easy confirmation. They are here one moment, gone the next, and no one can predict when or where one will occur. This irregularity has, of course, fueled more speculative ideas over the decades, from residual volcanic activity to the fanciful notion of observing lights from an alien outpost. Modern lunar orbiters and sophisticated Earth-based telescopes continue the hunt, but the flickers remain elusive. Each unexplained glow is a tiny reminder that the Moon is not entirely inert. It may still be breathing in its own slow, geological way, releasing pent-up energy from a turbulent past. This celestial puzzle, where light itself seems to glitch on the surface of our nearest neighbor, prepares us for an even more fundamental strangeness, one that warps the very fabric of time and space. Even time itself is not immune to the universe's strange inconsistencies. We know from Einstein's theory of relativity that time is not a constant river flowing at the same rate for everyone. A clock in a stronger gravitational field, like here on Earth, will tick more slowly than a clock in the weaker gravity of space. This is not just a theory, it is a daily reality for the global positioning system. The atomic clocks on board GPS satellites are programmed to run slightly faster than their identical counterparts on the ground, a necessary correction to keep your phone's map from guiding you into a lake. The math for this is precise and proven. Yet, when scientists push their instruments to the absolute limit, they sometimes find that reality and theory are not perfectly in sync. The Gravity Probe B mission, a masterpiece of engineering led by physicist Francis Everett, was designed to measure two subtle effects predicted by general relativity, the geodetic effect and frame dragging, by using ultra-precise gyroscopes in a near-perfect polar orbit. The spacecraft itself was a flying laboratory of timekeeping, and the data revealed tiny, stubborn discrepancies. The drift of its gyroscopes did not match the predictions with perfect accuracy. The deviations were minuscule, a fraction of a milliarcsecond per year. An angle so small it is like measuring the width of a human hair from over 300 kilometers away. But for the scientists, that tiny gap was a chasm. Could it be a simple, cumulative error in the complex measurement system? Or was it a whisper of something more profound? A hint that our understanding of spacetime curvature, the very fabric of the cosmos, is subtly incomplete. Experts have debated whether these minute glitches point toward an extension of Einstein's theory, perhaps an interaction with the mysterious pressure of dark energy that drives the universe's expansion. These are not just abstract puzzles. If time itself can waver in ways we do not fully understand, it has real consequences for the ultra-precise navigation required for future deep space missions and for our fundamental laws of physics. How can something as constant as time have these fleeting moments of ambiguity? The search for an answer forces us to look beyond isolated glitches and toward the universe's largest and most bizarre structures, where the rules seem to bend on a cosmic scale. Our own galaxy is not adrift in a random cosmic sea. It is being pulled along with thousands of its neighbors toward a specific point in the darkness, a gravitational monster we call the Great Attractor. Discovered in the 1970s through careful mapping of galaxy motions, this colossal anomaly lies in the direction of the Norma cluster, a region of space perpetually hidden from our optical view. It sits directly behind the dense, dusty plain of our own Milky Way, in what astronomers call the zone of avoidance. This is like trying to see a distant city through a thick, perpetual fog. For decades, the heart of this gravitational beast remained a complete mystery. How could something with the mass of tens of thousands of galaxies be completely invisible to us? Scientists like René Cron-Courtoeg led the charge to see the unseeable. Using infrared and radio telescopes, instruments that can peer through the obscuring cosmic dust, her team and others began to map the hidden structures. They found a wealth of previously unknown galaxy clusters, a veritable metropolis of stars and matter. Yet, even this vast congregation did not seem massive enough to account for the tremendous pull we feel. Our entire local supercluster, including the Milky Way, is rushing toward this point at over 2 million kilometers per hour. This motion is a profound glitch in the simple model of universal expansion, a coordinated drift on an immense scale. So what is generating this force if not the visible galaxies? The leading theory points to an immense concentration of dark matter, the invisible scaffolding of the cosmos, woven through the region in a way we cannot directly detect. It suggests that the Great Attractor is not a single point, but the dense core of a much larger structure, the Laniakea supercluster, a cosmic web of filaments where our galaxy is just one small thread flowing toward the gravitational center. This hidden beast challenges our maps of the cosmos, reminding us that most of the universe's influence is utterly dark, and that our journey through space is guided by forces we are only beginning to comprehend. But while gravity pulls on the grandest scales, the universe also glitches in the realm of the impossibly small, where particles behave in ways that defy common sense. The fabric of reality glitches not only in the silent drift of galaxies, but also in the furious impact of a single subatomic bullet. On an October day in 1991, a cosmic ray detector in Utah recorded something that should not exist. A single proton, later nicknamed the "Oh my God" particle, slammed into our atmosphere with an energy of over 300 electron volts. It was moving at 0.999999999999996 of the speed of light, so fast that in a race with a beam of light, it would have lost by less than a hair's breadth after traveling across the entire visible universe. This was not just a high-energy event, it was an impossibility. According to our best theories, particles from distant galaxies should hit a wall long before they reach such fantastic energies. This is the GZK limit, a theoretical cutoff named for its discoverers. As a high-energy proton travels for millions of years across the universe, it should constantly bump into the faint, leftover glow of the Big Bang, the cosmic microwave background. Each collision saps its energy, like a marathon runner constantly tripping over invisible hurdles. The "Oh my God" particle, and others like it, should have been slowed to a crawl long before they ever reached Earth. The fact that they arrive here with such staggering force means they either come from very nearby, which we have ruled out, or something is fundamentally wrong with our understanding of their journey. Scientists like John Matthews and teams at the massive Pierre Auger Observatory in Argentina have spent decades trying to solve this. They have cataloged a handful of these ultra-rare events, each one a monumental discovery. The leading suspects are the most violent engines in the cosmos, active galactic nuclei where supermassive black holes shred entire stars, or the cataclysmic collapses of massive stars in gamma-ray bursts. Yet, when they trace the apparent path of these particles back into the sky, they find no obvious source. The problem is that cosmic rays are not like light, they are charged particles. Their paths are twisted and bent by the magnetic fields that permeate interstellar space, making it nearly impossible to pinpoint their true origin. It is like trying to find the source of a river by following a single leaf that has been blown and tossed by 1,000 different winds. This leaves open even more exotic possibilities. Could these particles be the decay products of super-heavy dark matter, or the signature of cosmic strings, theoretical defects in the fabric of space-time? Each ultra-high-energy impact is a message from a cosmic catastrophe, but the message is scrambled, and we lack the code to read it. How can a single, tiny particle carry the punch of a professionally thrown baseball, all concentrated into a subatomic point? The existence of these particles is a glitch at the most fundamental level, proving that somewhere in the darkness, nature has accelerators of unimaginable power that we have yet to comprehend. And just as we grapple with these mysterious particles from the void, we find that the death throes of stars can produce signals just as baffling. Even the steady light of a distant star can flicker in ways that defy all logic. Far away in the constellation Cygnus, A Sun-like star named KIC 8462852, or Tabby's star, began to behave bizarrely. Data from the Kepler Space Telescope revealed it was not just dimming slightly, as a planet might cause, but plunging into darkness by staggering amounts, up to 22%. A planet, even a giant one, would only block about 1% of a star's light. This was something else entirely. A shadow so deep it suggested an object of impossible scale was passing in front of it. The discovery was made not by a professional astronomer, but by citizen scientists sifting through public data, highlighting that the universe's greatest secrets are sometimes found by dedicated amateurs. When astronomer Tabetha Boyajian led the official investigation, the mystery only deepened. The dimming was erratic, with no regular rhythm. It was not the clean, repeating dip of an orbiting planet, but a chaotic series of drops, some shallow, some profoundly deep, as if a swarm of irregular, light-blocking shapes were tumbling around the star in a complex dance. The immediate, most tantalizing hypothesis was that we were seeing the signature of an alien megastructure. The concept, first proposed by physicist Freeman Dyson, imagines a vast swarm of solar collectors built by an advanced civilization to harness the entire energy output of its star. Such a Dyson sphere, even partially constructed, would block starlight in these strange, unpredictable patterns. Yet, scientists are a cautious group, and they first looked for every possible natural explanation. Could it be a vast family of comets, shattered by a close encounter with the star, or a thick, warped disk of planetary debris from a recent collision? Each idea had its merits, but none could perfectly account for the sheer depth of the dimming or its chaotic timing. Then, another layer was added to the puzzle. Observations over several years showed that Tabby's star was not just dipping erratically. It was also slowly, steadily fading overall. This long-term dimming made the comet swarm theory even less likely. Why would the star itself be growing consistently darker? The debate intensified, pitting a revolutionary, almost science fiction idea against the stubborn refusal of the data to fit any known natural model. While most astronomers today lean toward a natural cause, perhaps an immense, uneven cloud of fine dust or the remnants of a devoured planet, the true nature of the obstruction remains unknown. The star's wild glitches force us to confront the limits of our stellar models, and to acknowledge that we may not yet have seen all the ways a solar system can form and evolve. It stands as a powerful symbol of cosmic mystery, a single point of light that asks a monumental question. Are we looking at a new type of astrophysical object, or the faint, distant signature of intelligence on a scale we can barely comprehend? This search for patterns in starlight finds a strange parallel in the ripples of spacetime itself, where scientists have detected gravitational waves with a peculiar and unexpected origin. The smooth fabric of spacetime sometimes wrinkles in ways that leave physicists speechless. When the LIGO and Virgo observatories detected a gravitational wave event known as GW 1951, they recorded the collision of two black holes of impossible size. Their combined mass was over 140 times that of our Sun, placing them squarely in a forbidden range called the pair instability mass gap. According to our best models of stellar evolution, a star cannot collapse directly into a black hole within this specific mass window. It should tear itself apart in a supernova so violent that nothing remains. Yet, the ripples from this cosmic crash were unmistakable. How did two black holes, each too heavy to form from a single dying star, come to exist and then find each other in the dark? This single event forced scientists to consider radical new formation channels. Perhaps these black holes were not born from stars at all, but are primordial, forged in the dense, chaotic first moments after the Big Bang. Or maybe they are the products of previous, smaller mergers, a chain of cosmic cannibalism within a dense star cluster. The anomalies do not end with mass. Sometimes, the gravitational wave signal itself carries a subtle twist, a distortion in its shape or frequency that does not match the clean predictions of Einstein's equations. Theorists like Nico Yunes and others explore whether these glitches could be the signature of exotic objects. Imagine a boson star, a hypothetical structure made not of atoms, but of ultralight, wave-like particles colliding with a black hole. Such an event would send a unique, shivering ripple through spacetime, one that our current models cannot fully replicate. Other signals show black holes spinning in perfect alignment, as if choreographed, a configuration that is statistically unlikely if they formed independently and randomly paired up. This points to them being born together in a binary system, or to merging within a turbulent, gaseous disk surrounding a supermassive black hole. Each unexpected detail is a clue, potentially pointing toward dark matter interactions or other cosmic processes operating in the shadows. Why would the universe's most violent events sometimes follow a script we have not yet written? These gravitational wave glitches are more than just data points. They are direct messengers from the most extreme realms of existence, telling us that our map of black holes and the forces that create them is still woefully incomplete. This fundamental uncertainty about the forces shaping our cosmos finds a parallel in one of the most heated debates in modern cosmology, a conflict over the very speed of the universe's expansion. Even the universe's most basic rhythm, its steady expansion, is now showing a crack in its foundation. For a century, we have known the cosmos is growing larger, with galaxies racing away from each other. We even measured the speed of this growth, a number called the Hubble constant. But today, we have two very precise, yet completely different, ways of measuring this speed, and they stubbornly refuse to agree. This growing rift is the Hubble tension, a fundamental glitch in our understanding of cosmic evolution. One method looks back to the universe's infancy. We study the faint afterglow of the Big Bang, the cosmic microwave background, with exquisite instruments like the Planck satellite. By mapping the tiny temperature variations in this ancient light, we can calculate how fast the infant universe was expanding and predict what the expansion rate should be today. This is like calculating how fast a child should be running as an adult based on a baby picture. The other method skips the history and measures the present directly. Teams like SH0ES use powerful telescopes to observe dying stars, called supernova, in nearby galaxies. These stellar explosions have a known intrinsic brightness, so by measuring how dim they appear from Earth, we can precisely gauge their distance and in turn calculate the current expansion rate. This is like using a radar gun to clock the runner's speed right now. The problem is, the runner is going much faster than the baby picture predicted. The local, present-day measurements consistently show the universe expanding about 5 to 10% faster than the pristine early universe data implies. This is not a small rounding error. It is a significant and persistent mismatch that has survived years of rechecking and refined data from brilliant scientists like Wendy Friedman. Could there be some hidden, systematic mistake in our measurements? Perhaps our understanding of the supernova themselves is slightly off. Or maybe there is some unexpected dust in local space skewing the results. But as the data piles up, the case for a simple error weakens. This has forced cosmologists to consider truly revolutionary ideas. Maybe dark energy, the mysterious force driving the expansion, is not constant as we assumed. Perhaps it is evolving, growing stronger over time, giving the universe an extra push. Other theories propose the existence of new, unknown types of particles that flooded the early cosmos, subtly altering the conditions we read from the cosmic microwave background. Some even suggest this tension is a hint that Einstein's theory of gravity needs a modification when applied to the universe as a whole. The Hubble tension is more than a technical dispute. It is a direct challenge to our standard model of cosmology. It suggests that our cosmic recipe The precise blend of ordinary matter, and dark energy that we thought explained everything might be missing a key ingredient. Why would the universe's most fundamental metric refuse to give us a single, consistent answer? This grand conflict over the speed of space itself forces us to look closer to home, where our own solar system holds puzzles of a different, more intimate kind. Far beyond the orbit of Neptune, the solar system does not simply fade into emptiness. It holds a vast, donut-shaped ring of icy worlds known as the Kuiper Belt, a frozen archive of the solar system's earliest days. Yet, this distant frontier holds a startling secret, a boundary so sharp it looks like a cliff edge on a cosmic map. When astronomers like those using the Subaru telescope began to census these icy bodies, they expected to find a gradually thinning population, with smaller objects scattered farther and farther out. Instead, they found a sudden and dramatic drop. Beyond a distance of about 50 astronomical units, the number of detectable objects plummets. It is as if the builder of the solar system simply stopped placing asteroids, leaving a stark and unexpected boundary in the void. This is the Kuiper Belt Cliff, a feature that no standard model of planetary formation predicted. How could a cloud of primordial debris left over from the birth of the planets end so abruptly? A natural, gentle thinning would make sense, but this is a hard stop, a genuine glitch in the architecture of our own cosmic backyard. The most compelling explanation involves an unseen architect, a gravitational hand that swept this region clean. Researchers like Konstantin Batygin, who also co-proposed the Planet 9 hypothesis, suggest this very cliff could be the signature of a hidden, massive planet. The gravitational influence of such a world, orbiting far beyond the cliff, could have shepherded the Kuiper Belt objects, ejecting some and pushing others inward, carving out this sharp edge over billions of years. Another, more dramatic theory posits a stellar passage, a time long ago when another star drifted close to our infant solar system. Its gravity would have been like a tide, stripping away the outer material of the protoplanetary disk and leaving behind this truncated belt we see today. Each theory has its merits, but the cliff remains a silent testament to a violent event or a hidden presence. This is not just a curiosity for astronomers. The structure of the Kuiper Belt is a direct record of the forces that shaped our solar system. Its sharp edge tells us that the peaceful, clockwork arrangement we see today is the result of a much more dynamic and chaotic history, one that may still include a major, undiscovered world lurking in the perpetual twilight. This mystery of a missing population at the solar system's edge finds a strange parallel in the very composition of the objects that are out there, where scientists are finding materials that should not exist. Deep within our planet's atmosphere, for a single brilliant moment, a visitor from another star revealed itself. On January 8, 2014, a meteor now catalogued as CNEOS 2014-0108 exploded in a fireball over the South Pacific. For years, it was just another entry in the fireball database, until Harvard astronomers Amir Suraj and Avi Loeb reanalyzed its trajectory. They discovered its path was not bound to our Sun. It was moving at over 130,000 miles per hour relative to the solar system, a speed so fast it could only mean one thing. This was the first known interstellar object to ever strike Earth, arriving 3 years before the interstellar object, Oumuamua, was spotted on its way out. The meteor's incredible velocity was a clear signature of an origin in another star system, a piece of cosmic shrapnel flung across the galaxy. But its strangeness did not end with its speed. When scientists calculated the material strength needed for the object to survive its plunge into the atmosphere at such a high velocity, they found it was unusually tough, likely composed of a substance harder than any iron-based meteorite we know. This extraordinary strength immediately sparked debate. Was this a new type of natural asteroid, forged in the heart of a dying star or a planetary collision in a distant system? Or, as some researchers cautiously suggested, could its unusual composition hint at something more engineered? Avi Loeb's subsequent expedition to the Pacific Ocean floor aimed to find fragments, searching for this unique material to answer the question directly. The natural explanations are compelling. It could be a shard from a planet torn apart by its star, or a piece of a supernova remnant, a type of cosmic object we have never before held in our hands. Yet the very fact that we are forced to consider such exotic origins shows how little we know about the materials that make up other star systems. This meteor was a tiny, fast-moving messenger, delivering a sample of the wider galaxy directly to our doorstep, but we were not prepared to catch it. Its brief flash left us with more questions than data, a frustratingly limited glimpse of what is traveling between the stars. What can this one rock teach us about the building blocks of other worlds? Its peculiar strength suggests that the cosmic palette of materials is far more diverse and resilient than we ever imagined, with other solar systems potentially building their planets from substances we have yet to discover. This fleeting encounter with a fragment of another star system shifts our perspective from the solid to the empty, from the objects we can see to the vast, inexplicable nothingness that surrounds them. The universe is not just a scattering of stars, it is a cosmic sponge filled with vast bubbles and voids. One of these voids is so immense and so empty it defies belief. The Boötes Void is a spherical desert of near-nothingness, a region of space so large you could fit tens of thousands of Milky Way galaxies inside it, and yet you would find almost none. Stretching over 330 million light-years across, this cavern contains only a few dozen galaxies where standard models predict there should be thousands. When astronomer Robert Kirshner and his team first mapped this emptiness in the 1980s, it shattered the prevailing idea that matter was distributed somewhat evenly across the largest scales. This was not a gentle thinning, it was a chasm. How could the universe, in its frantic early expansion, leave behind a pocket of such profound nothing? Cosmologists like Gregory Aldering have studied this void to understand the forces that shape the cosmos. The leading theory points to dark energy, the mysterious force accelerating the universe's expansion. In regions that were just slightly less dense to begin with, dark energy's repulsive push could have overwhelmed the weak gravitational pull, preventing matter from clumping together to form galaxies. It would have effectively stretched these regions into true cosmic deserts, but the void is not completely barren, and the few galaxies that do cling to existence within it are themselves strange. They tend to be isolated, often irregular in shape, and show signs of stunted evolution, as if they grew up in a place with no neighbors to influence them. This raises a haunting question: is the void truly empty, or is it filled with an invisible scaffolding of dark matter and faint, diffuse gas that we simply cannot see? The Boötes Void stands as a monument to the power of absence, a glitch in the large-scale structure of the cosmos that forces us to reconsider what nothing really means. And just as we contemplate this staggering emptiness, we must also confront the strange behavior of the very thing that allows us to see it, light itself. Light from the distant universe does not always travel in a straight line. It bends around massive objects in a phenomenon called gravitational lensing, where galaxy clusters act as cosmic magnifying glasses, warping the fabric of spacetime to create multiple, distorted images of the galaxies behind them. The math for this is precise, a beautiful validation of Einstein's general relativity. Yet sometimes, the mirror distorts in ways the equations do not predict. In certain clusters, the light is bent too much, or the lensed arcs appear in places they simply should not be, as if an unseen hand is tugging at the fabric of the lens. These are the lensing anomalies, glitches in gravity's grand telescope that reveal the shadows of the invisible universe. One of the most profound examples is the Bullet Cluster, a cosmic collision of two galaxy clusters. When astronomers like Douglas Clow mapped it, they saw something remarkable. The visible matter, the hot gas detected by X-ray telescopes, was lagging behind the collision. But the gravitational lensing effect, the map of where the mass actually was, had raced ahead. This was a direct image of dark matter, separated from the normal stuff. The dark matter, seemingly unaffected by the smash-up, had streamed right through, proving it is not just an abstract idea but a physical substance that interacts through gravity alone. But the mysteries only deepen on smaller scales. When scientists examine the intricate, jewel-like arcs of lensed galaxies in finer detail, they often find tiny, secondary warps within the larger distortion. The overall shape of the lens is correct, but there are kinks and extra magnifications that suggest the dark matter halo is not smooth. It seems to be lumpy, filled with unseen substructures, clumps of dark matter that themselves create miniature lenses. What are these invisible clumps? They could be the ghosts of smaller satellite galaxies that never formed stars, or they might be vast clouds of pure dark matter. Their existence is a critical test for our leading theories. The standard cold dark matter model predicts exactly this kind of lumpiness, but if the clumps are too numerous or too dense, it might point toward a more complex picture, like self-interacting dark matter, where these particles can occasionally bounce off each other. Another tantalizing possibility is that these tiny lensing anomalies are not caused by diffuse clouds at all, but by solid, massive objects. They could be the signature of primordial black holes, hypothetical black holes forged in the first second after the Big Bang, which could make up a fraction of the dark matter. Each unexpected bend of light is a clue, a way to map the architecture of the dark universe. Why does gravity's mirror sometimes show us a reality we did not expect to see? These subtle distortions are our only way to perceive the vast, invisible scaffolding that dictates the fate of the cosmos, forcing us to ask what truly holds the galaxies together. And just as these silent distortions of light reveal hidden masses, the violent death of stars can produce flashes of light with their own peculiar secrets. A star's final moments should be a predictable cataclysm, a final brilliant flash following a well-understood script. Yet sometimes the script is torn up right before our eyes. Consider Supernova 2014C. It began its death throes looking like one type of stellar explosion, a type I, characterized by a lack of hydrogen in its spectrum. Then, over a matter of weeks, it transformed. It morphed into a type Roman II supernova, suddenly showing a massive shell of hydrogen that had not been there before. This was not a simple explosion, it was a cosmic shapeshifter. Astronomers were left baffled, forced to conclude that the star must have ejected a huge amount of its outer hydrogen shell very late in its life, just a short time before it went supernova. It was as if the star had a final, violent shudder, throwing off a part of itself moments before the final detonation. This bizarre transformation points to a progenitor system far more complex than a single, isolated star, likely involving a companion star in a tight, deadly dance that stripped away layers of material in a final, chaotic act. Researchers like Alicia Soderberg study these events to understand the violent interactions in binary systems, where one star can effectively cannibalize its partner, leading to an explosion that defies simple classification. The anomalies do not stop there. Other supernovae produce staggering amounts of nickel-56, a radioactive element that powers the light curve, in quantities that seem physically impossible. Some explode in a profoundly lopsided manner, with shock waves breaking out of one side of the star long before the other, creating a bizarre, uneven flash. These are not minor variations, they are fundamental glitches in our understanding of stellar death. How can a process as catastrophic as a star's core collapse produce such wildly different outcomes? Each aberrant explosion forces us to reconsider the physics itself. Could some of these events be quark nova, a hypothetical implosion where the core condenses into a soup of even more fundamental particles, releasing a completely different kind of energy? The sheer diversity of supernova behavior screams that we are missing a crucial chapter in the story of how stars die and seed the galaxy with the elements for life. These explosive enigmas show that even in the most violent and final of acts, reality can still surprise us. And just as stars die in unpredictable ways, the invisible shields protecting planets can also begin to falter without warning. Even the magnetic fields of planets can be wildly misaligned, as if the universe assembled them incorrectly. Uranus stands as a perfect example, a world spinning on its side with a magnetic field that is equally askew. When Voyager 2 flew past the ice giant in 1986, its instruments revealed a planetary compass that was utterly broken. The magnetic field axis is tilted almost 60 degrees from the planet's axis of rotation, and it is not even centered on the planet's core. This is a configuration unlike any other in our solar system. On Earth, our magnetic field lines up roughly with our geographic poles. On Uranus, the magnetic poles are located closer to the equator, making its magnetosphere wobble like a poorly thrown top as the planet rotates. This bizarre arrangement defies our standard dynamo theory, which explains magnetic fields as being generated by the churning of conductive fluids in a planet's core. For Uranus, the dynamo itself must be fundamentally different. Planetary scientists like Heidi Hammel have proposed that the interior is not a simple, layered sphere. Instead, it might be a slushy ocean of water, ammonia, and methane ices, superheated and compressed into an electrically conductive fluid. This vast, turbulent sea could be generating the magnetic field from a shallow shell rather than a deep core, creating a field that is both lopsided and surprisingly weak. Another compelling theory points to a cataclysmic past. A giant impact early in the solar system's history could have literally knocked the planet over, disrupting its internal structure so profoundly that the dynamo never recovered its orderly spin. The consequences of this glitch are written across the space around Uranus. Its auroras are not neat rings around the poles as they are here, but diffuse, shimmering patches scattered across the planet, a direct result of the chaotic magnetic field lines funneling charged particles to unexpected places. The entire magnetosphere tumbles erratically, creating a space weather environment that is uniquely unpredictable. Why would a planet develop such a broken navigational system? The tilted mystery of Uranus forces us to reconsider how ice giants form and evolve, suggesting that their hidden interiors operate by rules we are only beginning to grasp. This profound irregularity in a planetary field finds a strange echo in the most ancient light of the cosmos, where scientists have detected a cold spot so vast it should not exist. Even the oldest light in the universe is not perfectly smooth. Embedded within the faint, uniform glow of the cosmic microwave background is a vast and profound chill, a region so much colder than its surroundings it stands out like a ghostly bruise on the sky. This is the cold spot, an anomaly spanning nearly 2 billion light-years, a cosmic void within a void that challenges our most fundamental ideas about the universe's birth. It was first identified with certainty by the Wilkinson Microwave Anisotropy Probe, and later confirmed in stunning detail by the Planck satellite, but its origin remains one of cosmology's most heated debates. The simplest explanation is that it is a supervoid, an immense and mostly empty region of space. As light from the cosmic microwave background travels through such a void, it loses energy climbing out of the void's gravitational well, a process known as the integrated Sachs-Wolf effect, which would make that patch of sky appear colder. Yet, the scale of the cold spot is the problem. It is overwhelmingly large. The emptiness required to produce such a profound chill is far greater than any known void we have mapped, pushing the limits of what our standard models of cosmic structure can plausibly create. This has led physicists like Laura Mersini-Houghton to propose a truly breathtaking alternative. She suggests the cold spot is not a structure within our universe at all, but a cosmic scar, an imprint from a collision with another universe in the multiverse. In this radical view, the energy drain from that primordial collision left a permanent cold patch on the sky, a fingerprint from a realm entirely beyond our own. Skeptics counter that it could be a statistical fluke, a 1 in 1,000 chance that just looks significant, or an artifact of foreground emissions from our own galaxy that we have not fully accounted for. But the cold spot persists, a stubborn glitch in the universe's first light. Is it a mere imperfection in the data, or is it a window into the multiverse, a direct glimpse of a cosmic architecture vaster than we ever dreamed? This search for patterns in the most ancient radiation finds a curious parallel much closer to home, in the rhythmic, clockwork dances of asteroids and moons. The silent gravitational dances of the cosmos are not always perfectly choreographed. Far out in the solar system, small worlds can become locked in an orbital embrace, their paths resonating with each other like perfectly timed gears in a cosmic clock. The most famous of these is the Laplace resonance, where Jupiter's moons Io, Europa, and Ganymede complete their orbits in a precise ratio. For every single orbit Ganymede makes, Europa completes 2, and Io races through 4. This gravitational lockstep keeps their orbits stable, but it also squeezes and stretches Io's interior, creating the most volcanically active body in the entire solar system. This tidal heating is a predictable outcome of a perfect resonance, yet sometimes the clockwork skips a beat. Astronomers detect tiny deviations in these patterns, minute wobbles in the rhythmic dance that hint at something deeper. These slight misalignments can be fossils of a violent past, suggesting the moons have migrated over billions of years, slowly settling into their current orbits after a long history of gravitational tug-of-war. Dynamicists like Renu Malhotra have used these orbital glitches to read the solar system's history. She and others have studied the Kuiper belt, that distant ring of icy debris, and found its own resonant patterns with Neptune. The planet's gravity has shepherded many of these objects into specific orbital periods, creating distinct groupings. But there are also unexpected gaps and clumps in this distribution, places where the resonance is either too weak or surprisingly strong. These anomalies are like footprints frozen in time, evidence of past perturbations. Perhaps a rogue planet once drifted through this region, its gravity scattering objects and disrupting the neat order. Or maybe Neptune itself migrated outward in its youth, its shifting gravitational influence capturing and rearranging the icy population as it moved. Each slight deviation from a perfect orbital ratio is a clue, testing our understanding of how stable multi-body systems can remain over billions of years. Why would a resonance that has held for eons suddenly show a subtle fracture? The answer forces us to consider dynamics we might be overlooking, like the collective gravitational pull of countless small, unseen objects or the lingering effects of ancient, catastrophic collisions. These orbital puzzles reveal that even the most stable-looking systems carry the scars of a chaotic birth, a hidden turbulence written in the language of mathematics and motion. Just as these gravitational rhythms can reveal a hidden history, the light from distant galaxies carries its own strange tempo, one that sometimes seems to beat out of sync with our understanding of the cosmos. Even the color of starlight can carry a hidden lie. For a century, astronomers have used redshift as a cosmic measuring tape, trusting that the more a galaxy's light is stretched toward the red end of the spectrum, the faster it is receding from us, and thus the farther away it must be. This relationship is the bedrock of modern cosmology, the very evidence for an expanding universe. Yet sometimes the tape measure snaps. In deep field images like the iconic Hubble Deep Field, Astronomers occasionally find galaxies whose redshift tells one story, while other clues tell another. A galaxy might have a high redshift, suggesting it is incredibly distant and should therefore be seen in its infancy, yet its structure appears mature and fully formed, as if it has aged faster than the universe allows. Or two galaxies that appear to be physically connected by a faint bridge of gas and stars can have wildly different redshifts, implying one is billions of light years behind the other. How can two objects be linked if they are not even neighbors? The late astronomer Halton Arp became the most famous challenger to the redshift consensus, compiling a catalog of these peculiar systems. He argued that redshift was not purely a measure of velocity and distance, but could also be an intrinsic property of a galaxy, perhaps related to its youth or a different kind of physics altogether. In his view, quasars with extremely high redshifts were not the faraway beacons everyone thought, but were instead being ejected from the cores of nearby active galaxies, their high redshift a signature of their violent birth rather than their cosmic distance. The mainstream astronomical community largely dismissed Arp's interpretations, attributing the strange pairings to chance alignments of unrelated objects or to subtle, local effects like the high-speed motion of galaxies within clusters. Yet, the anomalies he highlighted have never been fully explained away, lingering as stubborn glitches in the data. These spectral inconsistencies force a difficult question. Are we misreading the universe's most fundamental signal? If redshift can be deceptive, even in a handful of cases, it could mean that our entire cosmic distance ladder and the expansion history we've deduced from it rests on a slightly unstable foundation. This spectral mystery pulls our attention from the grand scale of galaxies to the rapid, precise ticks of the universe's most reliable clocks. Even the universe's most reliable clocks sometimes miss a beat. Deep in space, spinning neutron stars known as pulsars act as cosmic lighthouses, sending out beams of radiation with a rhythm so precise it can rival our best atomic clocks. Their steady pulse is a testament to the incredible density and stability of these stellar corpses, but occasionally, without warning, that perfect rhythm stutters. A pulsar will suddenly, violently, spin faster for a brief moment, a hiccup in spacetime known as a glitch. It is as if a spinning ice skater, with arms tucked in, were to inexplicably accelerate for a single turn before settling back into their original rhythm. This is not a gentle change, but a sudden jump, a fracture in the star's otherwise unbreakable routine. The Vela pulsar, one of the most famous and well-studied, has done this many times, its spin rate lurching upward in a fraction of a second. What could possibly make a city-sized ball of ultra-dense matter, heavier than our Sun, suddenly speed up? The answer lies deep within the star's bizarre heart. Astrophysicists like Andrew Lyne have dedicated their careers to listening for these stutters. The leading theory imagines the neutron star as a complex onion of different states. Its rigid outer crust, a crystalline lattice of atomic nuclei, spins at one rate, but inside, a superfluid sea of neutrons swirls with no friction at all. Normally, this superfluid is pinned to the crust, spinning along with it. But as the star gradually slows down over millennia, the superfluid, wanting to keep its original momentum, begins to spin faster relative to the crust. The strain builds until suddenly the pins break. Billions of vortices in the superfluid unlock all at once, transferring a massive amount of angular momentum to the crust in an instant, and the entire star lurches forward. Another possibility is a starquake, where the immense gravitational pressure causes the star's solid crust to crack and shift, much like an earthquake on Earth, suddenly making the star more compact and causing it to spin faster to conserve its rotation, just like that ice skater pulling their arms in tighter. Yet the precise trigger for these events remains just out of reach. Why do some pulsars glitch frequently and others rarely? Why are the jumps in spin so different in size? Each glitch is a unique message, telling us about the specific conditions inside that particular star, its magnetic field, its temperature, and the exotic states of matter that we cannot possibly recreate on Earth. These tiny stutters are our only window into the physics of a substance so dense that a single teaspoonful would weigh billions of tons. What strange phases of matter exist under that incredible pressure? The glitches themselves are the experiment, and the pulsar is the laboratory. This idea of sudden, violent reconfigurations in the fabric of reality finds an even more theoretical counterpart in the concept of cosmic strings, hypothetical cracks in spacetime left over from the birth of the universe. Beyond the sudden hiccups of pulsars lies a glitch woven into the very fabric of the cosmos, a crack in reality left over from its fiery birth. These are cosmic strings, hypothetical one-dimensional defects in spacetime, like the frozen cracks that form in ice. They are not made of matter, but are flaws in the geometry of the universe itself, infinitesimally thin but possessing immense mass. A single cosmic string, thinner than a proton, could stretch across the entire universe, and a loop of it just a mile long might weigh more than our entire planet. Their existence was first proposed in grand unified theories by physicists like Alexander Vilenkin, suggesting that as the hot, dense early universe cooled, it underwent a phase transition, and space-time itself crystallized with defects, much like flaws forming in a cooling crystal. If they exist, their effects would be as bizarre as they are profound. A cosmic string would warp the space around it so severely that it could act as a perfect gravitational lens, creating twin images of a single galaxy. If one were to pass between Earth and a distant star, we would see that star suddenly duplicate in the sky. Even stranger, the immense tension in a string could allow it to oscillate at nearly the speed of light, and if two strings crossed or a loop collapsed, it might release a titanic burst of gravitational waves or a flash of high-energy radiation, a signal unlike any known astrophysical source. The most mind-bending possibility involves a string's effect on time. The extreme spacetime curvature around a moving cosmic string could theoretically create closed time-like curves, pathways that loop back on themselves, opening the door to the potential for time travel. For decades, astronomers have hunted for these ghostly scars. They have scoured the cosmic microwave background for its unique temperature patterns and searched for the telltale double images of lensed galaxies. So far, every search has come up empty, yielding only null results. Yet, the hunt is not over. Unexplained anomalies in gravitational lensing surveys or strange features in the gamma-ray background keep the hope alive that we might be on the verge of a detection. Finding just one cosmic string would be a revolution. It would provide direct evidence for grand unified theories and give us a window into the universe's first moments, a time far earlier than we can see with any telescope. How could such an exotic structure, a literal crack in reality, glitch our understanding of physics? Its discovery would mean that the universe is not just expanding, but that its underlying structure is fundamentally flawed, bearing the permanent scars of its own violent creation. This search for the universe's fundamental geometry leads us to question the shape of everything, the overall curvature of the cosmos itself. The very geometry of the cosmos might be a glitch. For decades, the prevailing wisdom, etched into textbooks and supported by the pristine data of the cosmic microwave background, declared our universe to be flat. This is not flat like a sheet of paper, but flat in the language of geometry, meaning that parallel lines never meet and the angles of a triangle always add up to 180 degrees. This flatness was a key prediction of the inflationary model, a sudden, faster-than-light expansion in the universe's first moments that stretched spacetime into the smooth, Euclidean geometry we seem to inhabit. But the most detailed maps of the ancient light, from experiments like the Planck satellite, contain a subtle, persistent wrinkle. The power spectrum of the CMB, which charts the size and distribution of temperature fluctuations, shows a slight but telling anomaly. The data hints that the universe might not be perfectly flat after all, but instead possess a gentle, positive curvature, suggesting a cosmos that is finite and closed, like the surface of a four-dimensional sphere. Cosmologists like Eleonora di Valentino have pointed out that this signal, while sitting tantalizingly within the margin of error, refuses to go away. It could be a statistical fluke, or it could be the whisper of a monumental truth. If the universe is indeed curved even slightly, the implications are staggering. A closed universe would not be infinite. You could, in theory, travel in one perfectly straight line and eventually return to your starting point, having circumnavigated all of existence. This would fundamentally alter our understanding of the universe's fate, moving away from a perpetual, cold expansion and toward a future big crunch, where everything collapses back in on itself. It would also force a radical rewrite of our models for dark energy and inflation. Why would the cosmos present itself as flat, only to reveal a hidden curve upon the closest inspection? This geometric tension is more than a technical debate. It is a question about the very canvas upon which reality is painted. Is the universe an infinite, flat plane or a vast but finite bubble? The answer depends on whether this subtle glitch in the ancient light is a mere shadow or the outline of our cosmic prison. From the single red pen mark beside the WOW signal to the inexplicable drift of our own spacecraft, these cosmic glitches form a trail of breadcrumbs leading into the unknown. Each anomaly we have encountered, from the silent, tumbling shape of Oumuamua to the coordinated river of galaxies in the dark flow, serves as a profound reminder that our current understanding of the universe is a map with vast, unexplored territories. These are not failures of science, but its very engine, pushing us to question our most fundamental assumptions about physics, reality, and our place in the cosmos. They force us to invent new tools, to build better telescopes, and to dream of missions that can one day sail toward these mysteries. As Carl Sagan so beautifully put it, somewhere, something incredible is waiting to be known. These glitches are the signposts pointing toward that incredible something, beacons in the dark that guide us toward deeper truths. They inspire a fundamental curiosity that is the lifeblood of innovation, driving us to look harder, think deeper, and imagine bigger. What will the next generation of observatories reveal about the Hubble Tension? What will a probe sent to a future interstellar visitor discover about its composition? The answers are out there, hidden in the next flicker of a distant star or the next silent hiccup of a pulsar. If you have enjoyed this journey to the edges of our understanding, consider subscribing for more explorations into the universe's greatest puzzles. Let us know in the comments which of these anomalies baffles you the most. Thank you for joining us and keep looking up, for the next great mystery is always